Morning, everybody. Thank you for getting up that early and heading over here in Berlin on the Saturday morning. I'm going to be talking to you in this workshop hands-on how we can create records of scientific computation. So we're going to basically spend some time in the dry lab and we're going to actually run some experiments. And I think it was actually really good that the Bloxburg talk was just ahead of us because I think you've seen sort of the value of registering scientific results within organizations, but what if that could be done passively so that when scientists actually generate results, they don't need to actively hit a web portal and register it, but it just so happens automatically based on this products that they're using to get their work done. And this is what records do. So records is a platform that we're building. It grants ownership rights about the output of a computational tool that you're using, but eventually also a physical laboratory service that you're using. It has data analysis capabilities built in. It is a Python API, so you can just install that on your local laptop. You can run this in a Jupyter notebook, and you have access to some of the latest machine learning tools that are containerized, and they're running on top of a distributed storage and compute network. So this is very much sort of not proof of authority, but we're just using conventional storage systems and chains as well. So you can hit to try.lab.xyz in a moment, but before we do that, I'm going to give you a quick intro into how everything that we're doing here with records works. So records basically have three layers. The first layer is a storage layer. So we're not storing the information in any given university, but it's just living on IPFS, and then we work with protocol labs to move some of this data on Filecoin. And then we have a compute layer, and that's probably something that most of you have not yet heard about. It was launched about half a year ago. It's called Bacalhau, and it's a project that came out of Protocol Labs that allows you to run arbitrary containers over data that's pinned on IPFS. And then we have an ownership layer that basically captures the computation, the data that was used and the data that was generated. So on the storage side, I think most of you are familiar with IPFS. The strength of IPFS or any other peer-to-peer file storage system is that there's no server that you're relying on. There's no department server that you're relying on. There's not even like a Zenodo that you're relying on. The data is immutable and has unique identifiers. Now on the compute side, one big problem that you see in biology is that you have large data and very fragile code. So if you want to make sure that scientists have an easy time accessing the latest biomachine learning tools or just bioinformatics tools in general, you need to make sure that A, the algorithm runs where the data is stored, and then B, that you containerize the application because the dependencies get very exotic and it's hard to control the runtime. So what we've done is we've built on a framework for scientific workflows that is called the Common Workflow Language, and we have adapted the Common Workflow Language to run on Bacalhau and IPFS. Now, every scientist, every bioinformatician, every citizen can create and contribute a tool open source to the stack on our lab exchange by defining, here's a computational tool that I'm contributing. So this is, for example, a version of AlphaFold that can predict a protein structure. This is the input data that's going into that algorithm, and this is the output data that I'm expecting to see. So sort of in principle, you always have three different categories. You define your inputs, then you have a model that you're running. In this case, it's a protein structure prediction, but here it could be also making a pie, and then you have your outputs, and you're typing all of these things. And the nice thing about typing them is you can eventually chain them together. Scientists can build on the output of someone else. So in the case of, for example, small molecule protein docking, your inputs is a protein structure in a small molecule. The model is a method that explores the relationship between the two geometrically, and then your output is some kind of score of how tightly they interact. So the tools that we've onboarded so far are very much focused on computational biology. We have various tools for small molecule binding, various tools for protein folding and protein design, and there are also some more tools that you can check out in our docs. Now the third layer of this whole thing is that every time you run such a tool, every time you basically hit our Hugging Face for biology, you actually have an ownership token that represents, okay, I have the rights to this data. I was the one that actually ran this, had this idea, generate this output. So on the surface level, these are just sort of conventional NFTs, and if you then explore the metadata of the token, you see that you basically have this DAG that I just described, where you have the input function output relationship written into this. So instead of sort of just creating a certificate of, okay, this is a data set, and I registered that on chain, this is what a lot of NFTs are doing, this is also what Bloxburg is mostly based on, you're here actually having a complete functionalized representation where you actually have not only this is what I generated, but also this is how I generated it, and this is how you can rerun it too if you want to. Also, we have quite a bit of flexibility in terms of the license stack that we're giving the users. So right now, every time you mint such a token, it grants the owner an exclusive license to own the data, represent the data, that is also transferable and irrevocable. However, we can also swap the licenses relatively easily to have, for example, non-commercial use covered as well. We're right now working on basically creating the infrastructure to also bundle these types of records, so that when you run a scientific project, you're going to run more than one tool. You want to bundle all of these things together to eventually, for example, issue an IP NFT or some kind of sort of more commercially viable asset that represents the aggregate work that it was done. So what can records do? We're currently using records pretty actively in a couple pilots. We're using them in the drug discovery context for protein design. We're using them in drug discovery context with a biotech company for small molecule docking. We're also working with online scientific communities like VitaDAO to analyze some of the data from research projects that they have been sponsoring. And we also just recently worked together with Protocol Labs to move about, I think, 30 terabytes of protein data that was sort of threatened to be taken offline to the Filecoin network. So this was there was about 700 million protein structures that the Facebook AI research group generated. That team, however, is shutting down their bio department, and we took it on ourselves to move that data into distributed storage and make it available for the scientific community for good. Now, what can you do today? What can I do today? Is we launched about 30 days ago on testnet. We're right now on Optimism testnet. We have about more than 200 records that have been created so far. There are new tools being released every day. We also have ecosystem grants, so if you want to contribute a tool, if you have an application that you use in your research or a model that you're really passionate about, regardless, you can onboard it to the platform. It's getting easier by the minute, and we have grants available to support that. This is just one example that was launched this week. It's a protein binder design tool. So if you have, for example, a surface target related to a disease, these tools enable you to design a protein that can potentially target this and lead to a therapeutic. Do you want to try it yourself? If you want to, then you can head to the demo. The link that I would like you to head to is try.lab.xyz. And we're going to walk through it together here on the screen as well. So everybody who has a laptop, maybe just head to that notebook right now. And then show of hands, who has a laptop and wants to run a demo? So I also am here with Akash, and he can also help troubleshoot anybody that's running into issues. Okay. You're running it? Yeah. Okay. All right. Awesome. All right. Can you see? Is this large enough? Can you see the screen? All right, so this is just a conventional Python Jupyter notebook. And what we're going to be running is we're going to be running a protein folding tool. So the inputs to this recipe is a protein. We want to predict the structure of that protein. So the expected output is the actual 3D structure. And running this, first we will have to install the pip package. So this is our lab exchange package. You install it in your Python runtime. And then there's the next step. We need to define some parameters here. So we can basically decide what is the sequence of our protein. Maybe we just make some small change here. And then I need to add my wallet address. So where do I want to mint this? So let's look up a wallet that I can use here. So I'm just adding a wallet here. We can we submit this, and then we can take a look at how the code looks like actually under the hood. So we basically have three functions. The first function is a function in which we basically construct our request. This is what we currently call like an initialization step. Then there's a second step in which we then actually submit this initialized compute graph that we created. We submit that on the network. It then gets basically sent to a set of peer-to-peer compute and storage nodes. And then in the third step, once the computation is complete, we can then actually mint an NFT that represents that computational result. So let's submit this. And we can zoom into, what are the logs here. So we just sort of published our instruction after the initialization step on the IPFS. So this is our storage layer. And then we triggered a compute job. This is what this is doing over here. And now, well, obviously you have to be a bit patient because this prediction takes about 5 minutes to be completed. And then eventually, we actually have our input and output triplet complete, and we can actually mint a token and send that to our wallet. Now, what we're really excited about is that this is what I believe sort of the atomic unit of scientific activity that I can imagine. Like people still in their undergrad, playing with different tools, adding new tools, and similar to how you use Hugging Face right now to play with LLMs. I think playing with bio machine learning tools is something that we're going to see more and more of. And if people have a way to track their work and then even track the claims on the intellectual property to generate throughout the course, I believe that's a very powerful future to enable and make sure that it's also safe. So while this is still running, I can give you a bit of an overview of how this all looks like on chain. So this is currently our contract on testnet. And we can just look at one of these tokens. So it's an ERC 1155, currently in Optimus and Gurley, and we can explore some of the metadata, for example, here. And what we see is, for example, this is a token that was running a prediction, and we have here our input data. So we had a small molecule input and a protein that we gave as both as inputs, and then we dock those two against each other, and then we have the docked pose as an output. And we have all of this information tracked. So if we, for example, want to now look at one of these data, we can actually look at their content ID and we can pull on it. So I'm just putting up our IPFS gateway here. And this is, for example, here our processed protein from that computation that I can now download on my laptop if I wanted to, and I can take a look at. All of this is fully reproducible. And so we're now just going back to what we just ran. So this computation has completed. We're just downloading the results here, and we're going to be minting the token just shortly. Yeah, so it's minting the NFT. We have our NFT metadata that has just been posted. So we can just look at, again, just as I showed you a second ago, we can look at the token metadata. And then this is actually our protein that we just created. So we have our inputs. This is the sequence that we submitted, and then we have 5 different designs for proteins that we wanted to generate. And actually, we can visualize this thing ourselves here as well. There we go. This is your protein. You just minted an NFT, and you got your scientific result as you wanted it. Now the cool thing is you cannot only do this with one protein, you can do this with hundreds of proteins, because it's a peer-to-peer compute network, so you can basically scatter your jobs and scale them, parallelize them arbitrarily, just depending on how much compute is currently available. So we believe this is really not only a library to track your results, but actually just a library to like do Kubernetes on peer-to-peer and just scale up your computational applications as you want to. All right, everybody that like tried this, did it work on your end? Still waiting for it?
Getting feedback.
Okay.
Visualization.
Visualization? Okay. Akash, maybe you can just swing by and make sure everything is running. Okay, well, this is sort of it right now. So where do we go from here? We're super excited to like onboard more tools to this and increase the number of compute nodes on the network itself. Some applications that we're, for example, working on is like improved binary design. So this is actually helping for, I think, online communities that are interested in hitting new targets to mint valuable IP. And at the same time also increase the speed of it, so we can go from, okay, we want to mint one protein to like we can mint tens of thousands of proteins. And with that, I'm already at the end of this workshop. Happy to sort of stick around and help anybody who still wants to run this. And thank you for your time.